Today we are going to solve the problem 1.8 of Griffiths third edition Introduction to Quantum Mechanics. The problem 1.8 is suppose you add a constant V0 uh, to the potential. By constant I mean independent of x as well as t. In classical mechanics, this is not does not change anything. But what about quantum mechanics? That is very important question. So that the wave function becomes a time dependent phase vector exponential minus I V0 t over h cross. What does this have an expectation value of the dynamical variable? These are the question we are going to answer it. The original Hamiltonian is we know that h cat is equal to t cat plus v of x. That is total Hamiltonian is equal to the sum of the kinetic energy plus potential energy. Suppose after adding V0, that is a constant potential, the perturbed Hamiltonian H prime is equal to this unperturbed Hamiltonian plus V0 because V0 here applying some potential, but that is perturbation. The time dependent Schrödinger equation is for the perturbed wave function I h cross delta psi prime over delta t, which is equal to this perturbed Hamiltonian. That is h cat. H cat is unperturbed Hamiltonian plus perturbed Hamiltonian is unperturbed Hamiltonian plus V naught. So h cat plus V naught, which act on the perturbed wave function psi prime. Now we got the Schrödinger equation for perturbed Hamiltonian as iH cross delta psi prime over delta t, which is equal to h cat plus v naught psi prime. Assume the original solution, that is iH cross delta psi over delta t is equal to h cat psi. Here we have taken potential as 0. Let us consider the perturbed wave function psi prime of x and t, which has a time dependent component, and the wave function unperturbed wave function psi of x and t multiplied by the perturbation, which is a function of time f of t. Then compute its derivative. That is, you take a derivative of left hand side. That is delta psi prime over delta t is equal to first you differentiate the wave function delta psi over delta t and keep f of t as it is. Next, you keep psi at as it is and differentiate this f. Here you can see, notice that psi, I am differentiating this. This purely depends on t, not does not depends on position. So I have used full derivative. That is psi multiplied by tf by tt. But this psi depends on x and t, so I have taken partial derivative. So now you replace this here in this expression. That is delta psi prime over delta t is equal to this one. So you replace this right hand side here, left hand side of this equation. So this will become IH cross multiplied by delta psi over delta t f of t plus psi tf over tt, which is equal to this left hand side. I'm replacing psi prime as given here psi multiplied by f of t, and this Hamiltonian h perturbed Hamiltonian h cat plus v naught. Now we will try to simplify this. Now we got this expression. In the left hand side, you bring IH cross inside the bracket. Then this will become IH cross delta psi over delta t f of t plus IH cross psi delta f over, sorry, tf over tt. This is full derivative. And similarly here you bring psi f of t inside the bracket. So first term will become h cat psi f of t plus v naught psi f of t. Here, the first term I h cross partial t over tt is nothing but h psi from the Schrödinger equation. So you have f also here. So you can cancel this first term of left hand side and first term of the right hand side. And next you drop this psi from left hand side as well as right hand side. So this will become left hand side will become I h cross uh, df over dt is equal to this v naught f t. So we can bring I h cross to the right hand side, which will become minus I over h cross, because it's nothing but you are multiplying and dividing by I. So you will get minus I over h cross v naught f of t. So the general solution for this differential equation is f of t is equal to e power minus I v naught t over h cross. This is actually the phase vector. So we know the perturbed wave function is that is psi prime of x and t is equal to psi x and t multiplied by f of t, which is nothing but left hand side you keep as it is, right hand side you replace f of t by this one. So which is equal to psi of x and t e power minus I v naught t over h cross. Now we got psi prime of x and t is equal to psi of x and t multiplied by e power minus I v naught t over h cross. This exponential term is the phase factor. Now we will see this effect of this phase factor on expectation value. That is the effect on expectation value. So expectation value of the perturbed Hamiltonian can be written as psi prime star. Psi here psi prime star is you make it exponential term as plus, because you are taking the complex conjugate of this, which will become psi prime will become psi of x and t e power plus I v naught t over h cross. Then of course by definition expectation value is psi prime star a psi. So here psi is psi x of t e power minus I omega v naught t over h cross. Now this is a number you can bring back and forth. So this and this, if you multiply you will get 1. So ultimately you are getting integral of psi of x and t a psi of x and t. So here it is psi prime actually. Psi prime of x and t a then psi of x and t, which is nothing but the expectation value of a. So the expectation value of a prime, I have used prime here just to indicate the expectation value of perturbed wave function. So the expectation value of any dynamical variable does not change. The extra phase factor is global and cancel out in measurable quantities. Here, as I said, the phase factor is equal to e power minus I v naught t over h cross. If you find this lecture is useful one, like it and subscribe it in order to get my updated videos. Also join my channel for the growth of my channel. Thank you very much for watching my video continuously and supporting me. Thank you very much.